Hello everybody, my name is Denis Shilin. I'm a researcher at Federal Scientific Agroengineering Center WIM. My topic is determination of the optimal speed of movement of the conveyor belt of the prototype weight belt batcher.
The Russian Federation is a large center of the chemical and light industry, developing as such areas as the production of polymers, household chemicals, pharmaceuticals and medical preparations, the productions of rubbers, precious metals, chemical reagents, mechanical engineering and electrochemistry. Each production at one level or another implies continuous weighing of components for the manufacture or packaging of free-flowing mixtures. The weighing accuracy in this date directly affects the cost price and product quality. Dosing of components in a feed mill is an important technological stage. The dosage determines the volume of compound feed production as well as the quality of the feed produced. Product development is currently carried out according to recipes used on a computer, since experiment recipes are practically not used. Permissible error depending on the components included in the feed mixture. So, with a fraction of 30% or more, the error is less 1.5%. With from 10 to 30%, the error is less 1.0%. With a fraction less than 10%, the error is plus or minus 0.5%. When dosing mineral additives, the error is plus or minus 0.1%. Microelements, the error is plus or minus 0.01%. The main problems of technological processes, of model lines and the methods of dosing feed components used in them differ from the used feed mixtures as a rule by a justifiable high level of energy consumption. The solution to this problem is possible by improving the kinematic scheme of the installation by placing two strain gauges along the edges from the side of loading bulk materials. The goal of this work is to develop a prototype of a flow meter batcher which based on an improved kinematic diagram of two strain gauges for studying the dispensing error in the entire range of permissible plant productivity, from 5 tons per hour to 50 tons per hour. Project objectives: to develop the design of the flow meter batcher and develop a management system. This slide provides a description of the appearance of the flow meter batcher. As part of the work, design documentation was developed for a prototype of a flow meter batcher of various intensities, the appearance of which is shown in this slide. The presented installation simulates the operation of the flow meter batcher line, the adjustment of which is carried out by installing a unique flow section from loading side. The main structural elements of an inline flow meter batcher of various intensities are a metal frame and a design of a belt conveyor. In turn, the flow meter batcher body consists of the opening of the loading hopper 2, front wall 3, right wall 4, top wall 5, top cover 6, legs or supports 7, trays 10, 12 and 13, removable right cover 11, left wall 14, left removable cover 15, spherical support of the conveyor 16, twist lock 19, anchor bolt 20, stance 21, flow former 22, rubber seal 24, and handless 25. The conveyor belt moves by means of an electrical motor 9 through a gearbox 8. The main structural elements of the belt conveyor are conveyor belt 23, conveyor ball bearing 16, force sensor 18. The design of the unit has removable walls for maintenance. Each wall is rubber sealed around 24 to ensure a tighter seal. To remove the wall, loosen the twist lock 19 and use a handless 25. Anchor bolt 20 is designed to fasten and structure to the overhead crane for local movement and installation. The design of the conveyor in combination with force measure sensor 18 and ball bearing under the conveyor 16 is a kinematic diagram proposed by the authors, shown in the next slide. The kinematic diagram of the flow meter batcher consists of two strain gauges, D1 and D2, installed along the edges from the loading side of bulk materials, a dry drum on the shaft of which an asynchronous motor is fixed, a conveyor belt. The analyzer unit is designed to collect information from strain gauges. The technological process is controlled by an automatic control system, which ensures the dosing accuracy and productivity. As a rule, in a modern enterprise, a person is engaged in monitoring activities, fixing production errors, accidents, and other technological influences on various visualization systems. The main link of automatic systems is a controller cabinet, which, as a rule, includes a controller. The device contains in its memory the entire control program in the form of an algorithmization of the production process. The control cabinet of the developed prototype of the flow meter batcher of various intensities is shown in this slide. The cable duct, position 1 and 2, is intended for wiring. The DIN rail, position 3, holds all components that are securely fastened. The discrete input-output module 4 controls the discrete contacts of the printed circuit board 6. The analog input-output module 5 controls the analog contacts on the printed circuit board 6. A central processor 29 is installed on the mounting base 7, on which the program is executed. The communication module 12, which provides information exchange via the Ethernet interface. A dummy module 30 protecting the empty slots of the mounting base 7. The developed automatic control system module is conventionally divided into 3 levels: upper level, informational, basic level, manager, and lower level. Typically, each level has the following contents. Dispatch level. At this level, physical switches and routers should be installed, as well as software that allows the operator to work remotely from the production process. Middle level. This level is physically filled with controllers, expansion module for them directly by the program for controlling the technological process of the considered production. And lower level, which includes sensors, actuators, and other devices. This slide shows a diagram of an automatic control system for flow meter batcher of various intensities. The block diagram includes touch panel, programmable logic controller, frequency converter, encoder, strain gauge transducer, flow meter batcher, strain gauge, asynchronous motor, remote automated workstation, and cross cabinet. This slide shows the wiring diagram of the control system of the flow meter batcher. The router acts as a device for connecting to the network via Ethernet cables and Wi-Fi connections. On LAN ports is communicated between the following devices. The LAN 1 connector connects to the wiring board. The LAN 2 connector is connected to the WBB industrial controller. Connector LAN 3 is connected to the OneTech touchscreen graphic operator panel. As part of the work, a physical model of a prototype of a flow meter batcher of various intensities and an automatic control system providing both remote and local control of the installation were developed. The planned experiments with flow meter batcher of various intensities will make it possible to determine the optimal range of operating speeds of such installation and the margin of permissible error, the knowledge of which, in turn, will make it possible to form a calibration table of technical characteristics of flow meter batcher of various productivity and production intensity. It is also worth noting that the developed control system is scalable and its configuration makes it possible to integrate it into almost any production. This concludes my presentation. Thank you for your attention.